Welcome. In this video, we're going to prove the fundamental theorem of arithmetic using induction. And if you recall, the fundamental theorem of arithmetic tells us that every integer greater than 1 can be written uniquely as a prime or as the product of primes. So let's start. First, let P of n be the proposition that n can be written as a product of primes. And again, in case you forgot, n is an integer greater than 1. Great, so now let's start with our basis step. Now, P of 2, is true. Well, two things. Why did I start with 2? Well, the set of primes has a least element, and that least element is 2. So we started at our least element. And now, why is P of 2 true? Well, that's because 2 is equal to 2 to the 1 power, so we have just written 2 uniquely as a prime. Now let's look at our inductive step. So for this inductive step, we need to show that our P, starting at 2, and P of 3, and so on, all the way to P of k, if that is true, then this implies that P of k plus 1 is true for all integers k, or say for all integers j, such that 2 is less than or equal to j is less than or equal to k. Okay, so the inductive hypothesis is the assumption that pj is true for all integers within this with this restriction between 2 and k inclusive. All right, so that's our inductive hypothesis. And the idea is, what we're saying here is that we can write j as the product of prime numbers. So that's all our inductive hypothesis is saying, is that j can be written uniquely as a product of prime numbers, and j is at least 2 and is not greater than k. So it's sandwiched somewhere between 2 and k. It's an integer and it can be written as a product of primes. That's it. That's all our inductive hypothesis is asserting. Now we need to complete this inductive step. In order to do that, we have to show that this is true. So the kth plus 1 integer can be written uniquely as a product of primes. K plus 1 is an integer. There are two possible cases for k plus 1, and I'm going to scooch the screen up since I'm running out of space. So first we have case 1. K plus 1 is prime. If k plus 1 is prime, then that means we're done. And this is really similar to our basis step. P of k plus 1 is true, since k plus 1 can be written as k plus 1 to the 1 power. So we're done. Now let's look at case 2. And clearly, the only other possibility is that k plus 1 is not prime, so k plus 1 has to be composite. If k plus 1 is some composite integer, then k plus 1 equals the product of a and b, where a and b are sandwiched here between 2 and k plus 1. Now, since k is an integer and k plus 1 is an integer, clearly this inequality also holds. So what am I showing here? What I have is that a is a number that is larger than 2, but no larger than k. It might be 2, it might be k, but a is some number sandwiched between 2 and k inclusive. And I made a little typo here, so let me fix that. That should be a b. And I'm saying the same thing here. B is some number that is at least 2, but is not larger than k. Now we can use our inductive hypothesis. Our inductive hypothesis is that any number j between 2 and k has to be written as the product of primes. And a and b both meet that criteria. So if k plus 1 is composite, it can be written as a product AB. And furthermore, it can be written as a product of primes since a and b are both prime. So we could rewrite these both as their prime factorization. Since a and b are integers, both at least 2 but not greater than k, it follows by the inductive hypothesis that a and b can be written uniquely as primes. Thusly, k plus 1 equals a times b can be written as the product of the unique prime factorization of a with the unique prime factorization of b. And let me just fix a couple little words. Therefore, p of k plus 1 here is true.